Data class operations. Most operators do not work with data classes. Addition, subtraction, and the other math operations will not work, causing type errors. Similarly, the ordering operators, like the greater than and less than comparison operators, will not work. The equality and inequality operators do work, however. When you check if two data classes are equal, each field is checked in order to make sure they are equal. However, you will not often need to think about equality or any other operators with data classes directly. Instead, you should be thinking about accessing the fields of a data class in order to perform operations using the data stored inside of the data class. We have previously discussed how we can access the fields of instances in order to use their values. The syntax is quite simple. We have the name of the variable holding the instance, a period, and then the name field. This is similar to the syntax for a method, and that is no coincidence. Technically speaking, a method is just an attribute that holds a function. We will not bother learning to define methods in our data classes yet. Instead, the important thing to focus on is that we can access fields from instances. This is especially useful when we start passing data classes into functions. In the program shown here, we have moved the multiplication inside of a function to create a reusable area function that consumes a rectangle instance and produces an integer. Notice the rect parameter, which has the type rectangle, matching our previously defined data class. In the assert_equal, the parameter is matched to the corresponding argument, which in this case is the variable box. That box is containing an instance of the rectangle data class created using its constructor. Just to recap, we have a data class named rectangle, which is also the name of the constructor and the new type rectangle created. We can assign a constructed instance to a variable of our own choosing, which in this case was box. That variable can then be used as an argument to a function consuming a rectangle, like the area function. Inside of that function, we use the data class's type name on the right-hand side of the colon to indicate the type of the parameter. But on the left-hand side, we are free to give whatever name we want to the local variable holding the instance. We chose the name rect as a convenience, but could have chosen other names like lowercase rectangle or a_rectangle. As long as we are consistent within the function definition, the name does not matter to Python. From there, the function is able to use the fields of the instance to calculate and return the area. Notice how we only had to pass in one parameter to this function. Functions not only can consume data classes, they can also create them. In this example, we have a parse_card function that consumes a string value and produces a card instance. To do so, the function must call the card constructor and pass in the appropriate fields. In this case, that means the first character of the string as the first argument, and then the rest of the string converted to an integer for the second field. In the assert_equal, we call the function and then assert that the result is the same as calling the constructor with the literal values. In this way, we have a function that can return a data class. The utility of a data class is that we can bundle related fields together in order to represent a more complex object, and pass them conveniently around the program without having to have a huge number of variables. There is nothing special about the values stored in fields of instances. The attribute access expression using the period is no different than other expressions such as a variable lookup, math operation, or function call. That means we can pass the result of such expressions to other function calls, math operations, or even return them. In this example, we use the str function by passing in the values associated with the fields of the given rect instance, in order to create a nice string representation of the instance. One of the most useful but confusing aspects of a data class is that fields' values can also be changed later. In the example shown here, the stretch function consumes and produces the same rectangle. However, before returning the rectangle, its length field is doubled from its previous value. The syntax for updating the fields of a data class are almost exactly the same as updating the value of a variable. As we will discuss later in the section about mutability, there are many dangers to mutably updating fields like this. Therefore, we will look at an alternative. A common way to avoid mutation is to create a brand new instance with new values instead of updating the old instance. This may sound wasteful, but fortunately Python is quite fast about creating new instances. And in turn, we can use the new instance without worrying about the original being affected. If you want to see the tangible difference with this approach, try printing out the box variable at the end of the program shown here and the program shown before. In the mutable version, the original box variable is changed, while in this version, the original box is left untouched. Under what circumstances would you want to modify the original compared to making a copy? The trade-off might not be clear just yet, but for now remember that there are two ways to change a data classes, by making a new one based on an old one, or by editing the fields of an existing one.